Now, let us define these two important terms. That's excitation potential and ionization potential. And we have a nucleus and we have the orbits around the nucleus. Now, according to Bohr's theory, an atom, there are certain discrete energy orbits, stationary orbits, non-radiating orbits, in which electrons can revolve, okay, without radiating energy. So each of these orbits of a given atom is characterized by some definite energy. And we say that there are certain discrete energy levels. So this is an energy levels, discrete energy levels in an atom. And let us assume that an electron is revolving around the nucleus, and this electron in an atom, it absorbs some sufficient energy. It absorbs some sufficient energy from some outward source that's falling on it. And what happens is that it rises from its present position, a present energy level, to some higher energy level, right? And lasts there for a very short span of time, of the order of 10 to the power of minus 8 seconds. Now, after which this electron jumps back, it comes back to its ground state. It jumps back to the inner level, and thereby emitting energy, emitting the energy that it had absorbed in the form of electromagnetic radiation. Now, when an electron in this atom gains sufficient energy so as to escape completely from this atom, the atom is said to be ionized. We call it ionized, okay? Ionized. Again, when the atom recaptures, suppose the atom recaptures an electron and goes back to its original state where it was, the absorbed energy is emitted as electromagnetic radiation. So in case of transition from higher energy level to the lower, you will have the electromagnetic radiation. But if you give sufficient energy to this electron so that it completely loses the atom, we say that this atom is ionized. That's for sure. Now, the energy that we have calculated from Bohr's model of hydrogen atom, the energy that's required to excite or ionize a given atom is definite. It's perfectly definite. It's not anything in between. Now, for example, if we take the case of hydrogen atom and write down its energy in the nth orbit, so E nth is it's minus RhC by n square. Where this R is Rydberg constant for hydrogen atom, this is 1.1 into 10 to the power of 7. Then for Planck's constant, we have 6.6 times 10 to the power of minus 34 joules second. Then for speed of light, we have 3 times 10 to the power of 8 meter per second. Then we have n square. This is what we have, joules. And this nearly comes out to be 2.17 times 10 to the power of minus 18 times 1 by n square joules. And we can convert it into the electron volts by dividing this equation by 1.6 into 10 to the power of minus 19. And from there we get the value minus, we can write down here, this is 2.17 times 10 to the power of minus 18 by 1.6 times 10 to the power of minus 19 times 1 by n square electron volts. So on calculating this, what we get is energy of the nth orbit. So what we get is that this En is it is minus 13.6 electron volts by n square. Now this n is an integral number, and this n will have 1, 2, 3, and so on and so forth. So 1 will refer to the energy of the first level, second level, third level. And these energies, when you substitute in this equation, these energies will respectively come as, say, minus 13.6 will be for n is equal to 1. Then we will have 3.4 for n is equal to 2. And then we will have minus 1.51 electron volts for n is equal to 3, respectively, in all these cases. Now, the energy that we have to supply, we have an atom. The energy that we have to supply to the atom to raise an electron from, say, first orbit to the second orbit, that will be subtraction of the first two. That will be minus 13.6 minus this has to be minus 3.4. So we will have 10.2 electron volts of energy that's to be supplied here. So from first to the third, it will automatically go with this. And first to fourth, first, fifth, whatever the case may be. And to ionize the state, if I have to ionize this electron, I have to give the energy that is minus 13.6 minus 0. And that is 13.6 electron volts. If I reverse it, we can take the convention and have this 13.6 electron volts. Now the atoms are usually excited or they are ionized. That's the case by bombarding them with some particles. Maybe we will bombard them with electrons themselves. And we accelerate these electrons towards the atoms. Okay. Now the point is that the atoms are they are either excited depending on the quantum of energy that they have absorbed, or they are ionized depending on the quantum of energy that they have absorbed. Now the minimum accelerating potential that we impart to the bombarding electron to the bombarding electron, an energy sufficient to excite a given atom to some next state. We call that potential, that accelerating potential that we give to the electron to excite this electron from the first orbit to the second orbit or some other orbit. We call that thing as excitation potential. Now, excitation potential of this atom, and similarly the minimum accelerating potential which imparts to the bombarding electron an energy sufficient to ionize this, to get this electron out, to ionize this, to get it out, to get it out completely from an atom. This potential at which the electron that's being accelerated to get this electron out, we call this as ionization potential. So, if I have to speak about them in terms of numbers, then I will say that this 10.2 electron volt, or in other case you can find 12.09 electron volt, these are simply excitation potentials. These are excitation potential. This 10.2 is excitation. This is nothing but excitation potential. While this 13.6 electron volt that we have subjected, this is ionization potential for hydrogen atom. Now all these together, whether excitation potential or ionization potential, we call them as critical potentials. We call them as critical potentials. That's it. This is how we understand the excitation potential and ionization potential.